Hello everyone and welcome to yet another recreational programming session with Mr. Azote. So there's this very interesting algorithm which is called Byte-Pair-Encoding, and if you are a little bit into recent AI stuff and LLMs, you probably have heard about this entire thing. It's a way to tokenize the text for LLMs. Even Wikipedia actually says that a slightly modified version of this algorithm is used in large language model tokenizers. And what's up with tokenizers? So large language models don't really work on the level of each individual characters, right? Because to train a neural network to comprehend the text on the level of characters takes a lot of resources. So what they do instead, they actually split them into tokens, right? So one way to tokenize a text is by words, separate by spaces, but it's not particularly efficient way, right? So what they use instead is byte-pair-encoding, and it's actually a very simple and very smart algorithm at the same time. So essentially it tries to compress the text in some sense, right? So they have a pretty good example on Wikipedia, right? So I'm going to give the Wikipedia page to the chat, and for YouTube people it's going to be in the description. So you have this text, right? So and what you do, you kind of scan this text by pairs, right? So you scan this text by pairs. So I look at the pair AA, right, and I count that pair. Then I see another pair which is AA. I can see that that pair occurs twice, and then I continue scanning with this sliding window of 2. Right, I collect statistics of like what pair occurs most frequently, and I replace that pair with a single character instead of 2. Right, and now I have like a small table with one entry. Okay, so I replace them with Z, and Z is equal to AA. And I repeat the process again and build up this table. Right, and what's interesting about this table, so one symbol, for example, X in here, can actually mean 2 other symbols, then mean 2 other symbols. Right, so you sort of build like a tree or directed graph. Right, and that way you kind of compressed it and also figured out what is the most optimal way to split this text into tokens. And LLMs usually operate on these kind of tokens. So it's kind of similar to Huffman encoding, but it's not really Huffman encoding. So we haven't streamed Huffman codes ever, and I did code Huffman codes when I was in university, and it was super fun. I really like this algorithm, but I never actually streamed it. So maybe it's going to be one of the topics of the future streams. Thank you for reminding me about it. Thank you for reminding me about it. So yeah, and I really want to implement that, and I want to implement it for a very specific reason. So we have this bot. Which actually implements some simple Markov chains based on the logs of the chat, right? So you can do caret and you can say hello world, and it will try to continue the sentence, right? So based on the logs, right? And the way it works, it's pretty simple, right? So it just collects the statistics of like 8 characters and what's the most probable character that comes after that. So, and it's kind of stupid. It generates absolute freaking gibberish, as you can see. So it's not even that interesting. And what I realized after looking at the byte-pair-encoding algorithm is that it kind of implicitly builds up a grammar, if you think about it. Right. So do you guys know what is a BNF? BNF, Backus Neural Notation. Please in English, freaking $1 trillion company. I can't even figure out. $1 trillion company. Wikipedia. I'm so sorry. It's freaking unusable. Modern fucking internet is unusable. Like, what the fuck is this shit? Just like, it was never a fucking problem. This kind of shit was never fucking, I'm so sorry, but I'm so fucking pissed off. Right, anyway, so this is a Backus neural notation, and essentially what it describes is basically a syntax. You have this postal address, and postal address is a sequence of name part, street address, and zip part. Then you look, okay, name part is personal part, last name, and so on and so forth. You have this sort of relationship, what is what. And what's interesting is that the result of byte-pair encoding is a table that kind of looks like a grammar, but it's not coded by a human. It was derived, it was implicitly derived out of the text itself. So you can like look at that. So we have X, which is Z and Y, and what is Z? Z is AA, right? It's basically an implicit grammar, isn't it? It is literally just implicit grammar derived from the text. So, and once you have this implicit grammar, you can actually traverse this grammar recursively and generate random gibberish out of this grammar. Something that I think I did something like in BNF fuzzer, right? So let me actually see BNF fuzzer. Some time ago, I implemented privately, right? I streamed it a little bit, but then I couldn't market it properly. So I implemented just like in private. So this thing, which essentially parses BNF files, right? So let's take a look at some examples. So there is the postal code from Wikipedia. So here it is. Like it literally parses these kind of examples and then generates random text based on that grammar, so you can fuzz your parser if you want to, right? So I specifically implemented it to fuzz some of my parsers. I don't remember which one, but yeah. So once you have this implicit grammar that you derived from byte-pair encoding, you can kind of do the same. And it's going to be even cooler than just stupid Markov chains, right? So maybe it's going to be more comprehensible, but not on the level of LLMs, of course. LLMs is just like a next level. But what's funny is that, like if you think about it a little bit more deeply, LLMs store knowledge not only in the weights of their neural networks and transformers, their parameters, right? So they store information not only like in their parameters, but also in their tokenizer, right? There is a little bit of knowledge stored just in a tokenizer, simply in a tokenizer. Remove all of the transformers and the other shit, just the tokenizer already contains a little bit of that. Isn't it amazing? It's kind of cool, actually, if you think about it. I see it's like there is a Chomsky neural representation stuff. Maybe. I never read anything from Chomsky or Homsky, I don't know how to pronounce his name. But I heard that he's really into linguistic. He's the linguistic guy. He also likes to talk about politics on YouTube, but that stuff aside. So anyway, this is what I want to do. I actually downloaded some logs. I've been collecting logs on Discord. Right, so of people chatting and stuff like that, and I accumulated I think 30 megabytes of logs, and I think I want to try to build a BPE table, byte-pair encoding table, on these logs, and then just use it instead of my current Markov chains. So this is what I want to try to do. But first, we need to actually implement like a basic, compression of this text. I don't think I'm going to be able to finish this idea within a single stream. The last time I tried to do that, it actually takes more than 2 hours because there's a lot of like moving parts. You need to first compress the text, then we need some algorithm that, given the text, tokenizes it, and then we need to figure out how to use this grammar table to generate more text and continue the text. So I estimated to be like a roughly 3 episodes, right? So I estimated to be roughly 3 episodes, and on the first episode, I suppose we're going to be just implementing the algorithm of compression that, given the text, just generates you this table, right? And then on the next one, I think we're going to try to implement the tokenizer. Right, so essentially, given the text and given the table, split it into the tokens in the most efficient way. Right, so this is going to be rather useful for us, right? Because given the text, you will need to continue, so that means you will need to, tokenize it first, or at least, know the last token, right? So maybe you don't need to tokenize the entire thing. We'll figure it out. So, anyways, let's fucking start. Let's fucking start, meine Freunde. Fucking start. So, do I have BPE already? No, I don't have it. All right, because I already experimented with BPE before, but that didn't really go on YouTube. Like this session, I actually plan it to go on YouTube. So let's fucking go. We're gonna be using C, by the way. We're gonna be using a C, a mother flipping C. I'm so tired of using all of these meme languages and stuff like that. So I wish I could replace C, honestly, but every time I try to do that, like, it's just like, there's always something wrong with all of these languages. And C is not perfect by any means, but it's just, it's not perfect language, but it occupies the perfect niche, which is very difficult to replace it in. Assembly, here's the thing, people say assembly. Assembly is not a replacement for C because assembly is not cross-platform. C is cross-platform. That's the thing. Right, so there is a benefit of stripping off abstractions, but only at a certain level. After a certain level, you kind of not only stripping abstraction, you also stripping off the benefits. Right, so you need to be able to stop at some point, right? So you need to be able to stop at some point. So also people talk about C3. C3 is not finished, unfortunately, right? So it has a potential, but it has not realized that potential yet. We'll have to wait a little bit. So anyways, so maybe I'm gonna actually start using Knob, because we're gonna be using dynamic arrays. We definitely need dynamic arrays, and that means we'll need to use Knob because Knob has a dynamic array implementation, which is rather convenient. So here is the main thing. So I think I'm going to be calling it BP. So people who follow me on X know what the fuck I'm talking about. So, okay, so not everybody is on that stupid fucking platform, right? So there's this weird thing on fucking X, is that I made a short clip where I explained how to implement the I-append. It's a very short clip, like literally 2 minutes. And for some fucking reason, all of the grifters and AI bros are absolutely fucking fascinated by that clip and they keep reposting it. I have no idea why. And not only that, this clip, upon being reposted, being liked over thousands of likes all the time, and there's a meme going on X, people just repost dynamic arrays and see that clip of me. And I have no idea why. It's so bizarre. Because you're here because of the clip. What's so special about this clip? It's the most basic and boring data structure out there. Like, I honestly don't understand. I want to see the clip now. Just go x.com/sodding and there is one of the reposts. I also reposted it myself again as a meme. So anyway. So let's fucking go. So it's just like basically a clip where for 2 minutes I re-implement this macro. Right, so because I wanted to share how cool this macro is, because dynamic arrays in C are not a new idea, right? Dynamic arrays are not a new idea, but in many implementations in C, they're kind of overcomplicated, and I'm kind of proud that I came up with a very concise and small implementation of dynamic arrays, and I just wanted to share. I didn't expect that it's gonna take more than 1,000 likes, right? So just like, yeah, it's a pretty cool thing, but I didn't expect it for people to make it like, to constantly repost and stuff like that. So that's kind of weird. But anyway, so here is the thing. And I suppose I also want to implement knob.c, which is going to be the builder of an BP, I'm sorry. So let's include knob.h, and obviously I want to define knob implementation and a strip prefix. Right, so strip prefix, and let's do the usual thing. Return. Obviously, you need to do args and argv. So knob, go rebuild yourself, right? Otherwise, it's not going to go rebuild itself, and we need it to rebuild itself. So this is going to be CMD, right? So maybe let's make it global, right? So because we're going to be having only one instance of CD anyway, but maybe not. Actually, I'm not sure if it's a good idea in general, right? So it kind of makes me anxious, right? Even though I know that there's nothing really wrong with global variables if the scope of your program is small, still years of propaganda of good practices and shit like that kind of makes me anxious when I do that. So let's not do that. So I'm going to do append, and what we're going to be doing in here, we're going to be just like building the whole thing, right? So with all of the possible warnings, maybe also with debug information in case we want to debug something. And I'm going to just like create this entire thing. So this is going to be BPE, and this is bpe.c. Maybe I should do that in a separate build folder, chat. Yeah, right. Recently, I like to create a separate build folder. Build folder, right? And it's going to be just build slash. So, and the thing I have to do, I think, it's make dir if not exists. So I'm going to put the CMD in here. and just create the build folder. Just create the build folder, and if you failed, just exit with non-zero exit code. So then what I'm gonna do is create this executable in the build folder. Then we need to run the command that we just created, cmd run synchronously, obviously, and reset. That's the function I'm looking for. That's the function I'm looking for. Just run it and reset it. It may fail. Let's check for that. And if it failed, return 1. There you go. There you go. So let's bootstrap the build system as usual. It didn't bootstrap itself, right? So let's go through all of these things. What exactly happened? So here's the stack trace. I forgot to provide the CMD. Look at that. Look at that. Thank you, compiler. Very cool. All right, and it compiled. And now if I try to run this entire thing, it created the build folder and it created an executable inside of this build folder. Can your CMake do that? Can your CMake do that? It cannot do shit. You have to create build folder for CMake yourself manually. That's how fucking pathetic CMake. Anyway, doesn't matter. Like, I'm just joking. So, and let's just try to run BPE. It doesn't do shit because we said don't do anything. All right, so let's actually have maybe some text, right? So we're gonna have something like text, and we're gonna start with something simple, right? So let's not jump into trying to compress like 30 megabytes of logs or anything. Let's start small, right? So the quick brown fox jumps over the lazy dog. The quick brown fox jumps over the, well, that's this is the worst, well, maybe not actually. Maybe this is not the worst thing to do. Does it even have a repeating pairs? I feel like it doesn't have repeating pairs. Right, so I don't even know. We can try to compress something like this. So let's just take this text and try to compress that specifically. Right, so this is from Wikipedia, and let's say taken from here. Okay, so what we want to do, we want to be able to iterate it like pair by pair. So how are we going to be doing that? I need to maybe have a size of the text. So text size, strlen text. There you go. We have the size of the text. So now we're going to be iterating character by character, but we actually have to stop. I think we have to stop at the like at -1. Right, so because look at that, we're going to be iterating, and we're going to be also looking ahead to the next character because we're iterating by pairs, right? So then we increment by 1 and we're looking at that pair, and it's kind of dangerous if you go here and you try to look ahead, you have a buffer overflow, right? So you have to be a little bit careful in here. And another thing in here is that text size, if it's equal to, I suppose, 0, right? So if it's an empty text, it's going to underflow. And this is kind of dangerous. Maybe because of that, I want to make both of these things integers. Yeah, so I was always using size t for my iterators and sizes, precisely because they're unsigned, and size kind of is supposed to be unsigned. But for these kind of situations, I think making the size signed kind of works out, right? So you have a text 0, and there will be no iteration in here, right? Because there's no underflow. Right, it can go below 0. And what's interesting is that I got this idea from Jai, actually, believe it or not. So Jai, for whatever reason, uses signed integers everywhere for sizes and indices. And it constantly taking advantage of this kind of situation where if your size is equal to 0, it will become negative. And because of that, the iterator is not going to go up or anything like that. Because if it was unsigned, it would underflow and become the maximum value. So it's going to be iteration that goes to infinity. Not to infinity, but to the maximum value of 64-bit integer. So I'm kind of growing on not using unsigned integers when it comes to sizes and iterators. Right, so yeah, it's kind of interesting. Have you ever used string.h? So I'm using strlen. strlen is located in string.h. Anyways, so let's fucking go. What we're going to be doing in here, is we need to take like 2 characters in here. So it's going to be A, text I and B text I plus 1. So here they are. And let's just print them, right? So here's one character, here's another one, A, B. So, and let's just rebuild the whole thing. And there we go. Here are the pairs. Here are the pairs that we got in here. Isn't that cool? I think that's pretty cool. I think it is in fact pretty cool. So what we need to do next, we need to actually collect statistics of what pair occurs the most frequently, right? So to do that, I think the easiest way for us to be is going to be to use some sort of a hash table, right? So I don't really have a hash table implemented in Knob yet, so I think I'm going to go and just take the one from STB. So STB has a pretty cool hash table implementation, so which we're going to utilize in here. So this is going to be a row, and let's just download this entire stuff. wget, boom, and let's fucking go. So here it is. stbds, it's a single header library, similar to Knob, right? In fact, I got the idea of Knob from STB, so that means we'll have to include some stuff like stbds implementation. Yeah, exactly. So this is basically what we have to define in here. There we go. And the way it works, actually, you have to define a structure with two fields, right? You have to just define a structure with two fields. So let's call this structure maybe something like pair, right? So it's going to be like pair, but I'm honestly not sure, right? So it has to be, let's call it KV. It's a key value. So the first field is called key. It must be called key, and the second one is going to be value. And the type of the key is the type you want to have for the key, so the type with which you want to index your table, and the value is exactly what you want to index, right? In our case, I think the key is going to be the pair, right? So it's going to be the pair. So I think because of that, we have to make the key an array of two characters, right? So it's going to be an array of two characters, and the value is going to be, I guess, size t. Right, so it's like how many of them. And essentially, if you want to create like a hash table, some sort of like a frequency table, you create a variable which is a pointer to that KV, and this is going to be like a frequency, right? And let's initialize it with 0. And this is your hash table, essentially. This is your hash table. And the way you work with that hash table, you have a bunch of macros in this entire thing. So something like hm, like put, right? And this enables you to put some sort of a key in here. So you put like a frequency in here, and then you put a key in here. We need a way to actually combine these two things, right? So one of the things we can do is that we can say key to, right? So this is the first character, and this is the second one, right? Something like that, right? So, and we're gonna just like put this key in here, and the value is gonna be like, we'll probably first have to query it, get it out of the table, right? So which with something like hm get, right, it will enable us to get it. So usually we probably want to use hm get I, right? So we do something like this. We take the frec, we take the key, and it's supposed to return an integer ptr diff t. So this type is an integer. This type is an integer. You can even Google it up. And it's a standard integer, by the way. It is a standard integer. And I think it's a signed integer. So it's a signed integer type of the result of the subtracting two pointers. So when you subtract one pointer from another, the type in standard C is ptr diff underscore t. Right, and it's just like an alias to the corresponding suitable integer type. So that's what it is. So then you can use this particular index to index your specific slot, right? Your specific slot, and get a value out of that. So you're getting the value out of that. So this is going to be something like count, right? So here we're querying that specific key, and we get a count out of that, and then we want to increment it. We put it back, right? We put it back. Maybe since it's a value, I feel like we could have just maybe incremented like that, right? So we don't really have to use hm put ever, right? So we don't really have to use hm put. We can just like increment it and continue. But what's interesting is that the key might not exist in in a hash table. In that case, according to the documentation, it returns -1. So we can check if it's less than 0. That means we have to insert a new element in there. Let's do put frequency key, and we're gonna just insert 1. And otherwise, we're gonna increment it. I think that's fair. I think this is actually a pretty good way of doing that. So, and this is how we're gonna be doing all that, right? So here's the key. Here's the key. We created the table, then we either create in 1 or incrementing by 1. So that's about it. So after that, we can iterate this hash table and just print basically the statistics, right? So let's just print the statistics. So, and you can simply iterate this array, right? So this pointer as an array. So as far as I know, the elements are stored there sequentially. So there's no hole in them, which is kind of weird for a hash table. To be fair, usually when I implemented the hash tables there, they usually have some sort of holes, right? So you kind of have to be a little bit more careful, but in this implementation, you can just iterate them and they're sequential. So I don't really know how exactly it achieves them. I should probably read the implementation of this hash table. But anyway, so what you can do is basically get HMLen, right? So let's take HMLen, it's also PTR-diff. And it will give you just the size, right? So maybe we're going to use PTR-diff in here, which is I, 0, less than HMLef, frequency, plus I. So, and in here, we can just print all of that stuff. So this is going to be double that, and then ZU, which is the size. So, and in here, we can do freq I, key, 0. Then we need to take the second one, like this. And then for the frequency value. Right, and that should print all of the statistics for this entire stuff. Okay, so we didn't compile. Let's go to the compilation here. So we have some stuff in the macros. Let's follow the stack trace and see what the fuck is going on. In expansion of macros, so it really didn't like right, hm get frec, but frec is actually yeah. So I didn't really know what's up with that. What you don't like. Char makes integer from pointer without cast. Char from pointer. Is that because key is not really a pair? I was actually afraid that this may not work. I have a strange feeling that the way I have to do that is actually something like this. We can call it pair, right? So this is the pair, and I can just do something like that. So this is a key pair. Will that work a bit better? It may, right? So let's do pair. So this is the pair, and in here, what was the field? It was just a pair, right? So we can do something like that, and then we get it by the key, which is the pair, pair. Right, so I feel like just because it was an array, it might have broken some of the macros in there, right? So, but if we make it like a struct, it becomes sort of like a solid value, so maybe it will work now. Yeah, okay, so it doesn't work in here, so this is the key, and this is pair. We have to do something like that now, pair. I was right. I hate that I was right about that. Right, so stupid freaking C. Like, I swear to God, like, why do we still use this language? Like, there's no a proper C killer yet, unfortunately. Still no proper C killer. As you can see, here are the frequency of all of these things. Unfortunately, it is not really properly sorted, but I don't know. So maybe we can actually implement some sort of a sorter for this entire thing. So basically, frec is a pointer to some memory segment, and macro is managing it. Exactly. In fact, it is using a very interesting trick, right? So essentially, frec points at the beginning of the array that stores your slots of the hash table. But then, behind that pointer, it actually stores the header where it stores the additional meta information. So the way the macros work, they take this pointer, then they loop back to get that meta information, and then they find the rest of the stuff needed to manage the hash table. But for you, it looks like a regular pointer. But there's a lot of magic behind that pointer. So you have to be a little bit more careful when you use this kind of hash table. All of that is needed to make it more convenient to use, but in reality, it's not a classical C array. There's a little bit of a magic in there. unfortunately, because I personally hate magic. Right, but I mean, maybe you need this kind of stuff for the hash tables in C. Anyways, so one of the things we can do in here is maybe create a dynamic array of KVs. First of all, I think KV is not a particularly good name for this stuff. I'm gonna call it frec, right? So this is basically a frequency. So then maybe I can create something like frex, which is going to be a dynamic array of frec. Because what I want to do after I created a hash table, I want to copy it to a separate dynamic array and then sort it within that separate dynamic array with qsort or something like that, right? So because I want to actually you know, find the maximum. I want to find top 10 of them and see what's the most frequent pair, right? It's not going to be needed for the algorithm, but I just want to do that because I want to like see that. Right, so we're going to be implementing dynamic arrays. So let's fucking go. This is a frec, this is items, size t count, capacity. Right, so this is the frex. And in here, I suppose I'm going to do frex. And I'm going to call it sorted frex. So this is sorted frex, and originally it is 0. So after we collected the statistics, what we have to do, I suppose, we need to di append these things, these frex, into the sorted frex. Sorted frex, take it by the pointer, put this thing in here, and there we go, we collected them in here. After that, we need to sort them. So the standard library of C luckily has a qsort function, which actually allows us to do that. Look at that. We have to provide a pointer to where the array we want to sort starts, and it starts at sorted frex items. So here, if I remember correctly, is the amount of elements you want to sort. All right, so this is going to be sorted frex count, and the size is the size of the element in bytes. Right, so we're gonna do sorted frex item. I need to items. There is several of them. We're gonna dereference them, and we're gonna take the size of that specific type. The reason why I do that is because I want to be independent from the specific types in here. If in the future I will change the type of the items, I don't have to change this specific place, right? Because it doesn't care about the type. So here is an interesting thing. Now we need to provide a function, a pointer to the function that compares the frex, but we need to compare them in sort of like an opposite direction. So how can we do that? I think I'm gonna call the function compare frex, right? So I don't know how else would I call it. Compare frex. Compare frex. So here we essentially take two pointers. Actually opaque pointers, void pointers. The first thing we need to do, we probably need to cast them to pointers to frec, right, to be able to extract some information out of them. So this is going to be frec, pointer, let's call it AF. So this is that, and this is going to be BFB. There we go. So we have two pointers, and we can access their values. We want to sort them by the value, right? So this is going to be AF value, and this is a classical comparator, which returns a 0, right? Which returns an integer, right? And it returns three main values, -1, 0, and 1. And it's really mind-bending for me personally to figure out what each number means what. But if I remember correctly, the main idea behind these comparators, which return -1, 0, or 1, is that you do compare A and B. And if A is less than B, that means this entire thing has to be less than 0. So essentially, you must put the sign in here, the same that you would put between A and B. This is the idea behind the design of all of these comparators, right? So you probably encountered this kind of comparators in all sorts of languages. I think C started all of this meme, right? And then people started to like repeat that meme on all of the other languages. So the idea was that. All right, so you want to put some sort of a sign in here, and you need to return such integers so that you move that sign in here and it makes sense, right? So how I want to actually compare this thing, I want to build them from the biggest to the smallest. Because of that, I need to actually compare them like this, right? So I'm looking for the elements that are bigger than the rest of them. So because of that, the symbol in here has to be that. How can I achieve this kind of symbol? Well, so essentially, I need to maybe subtract value like this, right? Because if A is bigger then B is going to be positive value. It's going to be positive value, so that will work out. I think that's how we're going to do that. So if they're equal, it's going to be 0. And if A is smaller, it's going to be a negative value. Okay, I think that will work out. But we have to be a little bit careful because value is a size t, which is an unsigned integer. So because of that, we're prone to overflows and underflows. So let's actually first cast this entire thing to integer. Let's make it signed first. And then we can do the this kind of stuff. Hopefully I didn't make any mistakes, because working with these comparators is always mentally difficult for me, right? So because I can't comprehend how this entire stuff works, right? So, but maybe I did it correct this time. We'll see, we'll see. If I didn't do correct this time, I can always swap these two elements and that will be correct. So there's no reason to fuss about it too much, right? Anyways, so let's actually iterate the sorted array. So going to be 0 less than sorted fracs count plus I, and let's just print this entire stuff. So I should have not deleted the code that printed all of that stuff, but I mean, whatever. So this is ZU and sorted fracs items I. Then I have to take the key 0. That's a very long ass expression. So maybe what I'm gonna do in here, I'm gonna just do frac like this. I'm gonna be frac pointer to frac, boom, and I'm gonna just take a pointer to this entire thing. So that's a little bit more manageable. That's a little bit less hairy. Okay, so now this is the value, and hopefully that is going to work. Let's fucking go. That didn't compile. Let's see why. Because I have some garbage in the code. Okay, so what else do we have in here? This one is a pointer. Thank you so much. Thank you so much for not implementing auto dereferencing for the things. So the append, yeah. So we don't have a dir append because it is implemented in knob. Let's include knob.h, and in here I'm going to define knob implementation, and obviously also I want to strip the prefixes, otherwise I have to put that annoying knob everywhere. Okay, so it's almost worked. I think it's more like pair in here, right? So this is what I have to do, pair. Okay, and it worked. And I was wrong, as you can see. I fucked it up. So essentially to sort it in a different order, I have to do it like that. Right. But it's not a big deal, right? It's super easy to then just invert that, and there you go. We have the thing sorted. So now we know top 10. Now we know top 10. We can even like literally print top 10 in here. So this is going to be something like this, like print only the first 10. Yep, that was super easy. And according to the algorithm, this is the pair that we now have to replace with something else. So this is what we have to do. Okay, let's take a look at some subs. Let's take a look at some subs. Oh, that's a lot of subs actually. Thank you so much, Blink Dynamo for Twitch Prime. Redman Plus, thank you so much for tier 1. Howard Rourke 11, thank you so much. Geos MC, thank you so much for Twitch Prime. With the message, can't stand ads. Had to sub. Love from Italy. Thank you so much. The Space Herper, thank you so much for tier 1. And Lucas for 4589, thank you so much for Twitch Prime with the message. What do you use to debug memory leaks? Something like ASN and Walgrad? Yes, both of them. So it's just like depending on which one works for me, I just like use both of them. Usually, but detecting memory leaks with Valgrind is kind of difficult because the definition of memory leak is kind of fuzzy, unfortunately. What is a memory leak, chat? What is a memory leak? So if you define memory leak as something that was not freed before exiting the program, that's kind of a useless definition, because that's the shit that happens all the time and doesn't cause any problems, because people quite often just pre-allocate the fixed amount of memory that they use for the entirety of the program, and then they exit without deallocating this memory. So technically, because of that definition, it is a leaked memory, but in reality, it is not a leaked memory. So in fact, defining leaked memory is very difficult. In reality, it is very difficult to define what is a leaked memory. You can use the definition of garbage collectors, right? So which is basically unreachable memory, but that is a little bit better definition than just memory that you didn't free until the end. But it also has their own problems. For example, D programming language has a garbage collector. But it has a limitation because it's a system programming language and it allows you to work with pointers directly. You can potentially mess with those pointers. So what it does, it scans the memory, right, and looks for integers that looks like a valid pointers to the memory, right? And because of that, it considers the object under such pointer as reachable. Right, if you start messing with the pointers to the point that garbage collector cannot recognize that pointer, right, it will basically clean up that memory because it became unreachable, but in reality it wasn't unreachable. One of such things could be Zor linked list. Do you guys know what is a Zor linked list? Zor linked list. It's absolutely useless thing, but that's besides the point. The thing about Zor linked list is that it takes a Zor operation between the pointers. So the number that stores 2 pointers is actually an invalid pointer, and that trips off the garbage collector of D. So, and basically the D developers recommend to not do any of such tricks because it tricks a garbage collector into thinking that those objects don't exist anymore, and it will clean up your linked list. So again, reachability is a better definition, but it's not useful in system languages where you have a direct access to the pointers because you can mess with the pointers. Furthermore, quite often in JavaScript, for instance, not a system language, right, JavaScript, you may forget to clean up some of the callbacks that hold pointers to some things, and because of that, the usage memory is kind of growing because the objects that should have been unreachable still reachable. You have a garbage collector, you have a good definition of memory leak, you're still leaking memory. The memory consumption is growing because the things that should have not been reachable are reachable, and you're still back to thinking about memory management. Like, there's no good definition of a memory leak. That's the thing. Memory leak is kind of a subjective thing. If you start thinking about what is memory leak deeply, you will realize that what the fuck is a memory leak? Right, it's just like, it's more like an intent, but an intent is a subjective thing. So, you know what I'm talking about? It's kind of difficult, right? So when you only start in programming, it feels very easy. Oh, you just like, you forgot to free. No. It's actually kind of more complicated than that. Are you saying that memory leak is a social construct? It kind of is, in a sense. Probably because memory allocation is an artificial construct. It is kind of an artificial construct because on the level of computational model, basic fundamental computational model, what you have a head, you have an infinite tape, and you have the whole tape at your disposal. Where is the memory allocation, deallocation in that computation model? This is a construct that we put on top of the fundamental computation model, right? So, and in reality, if you take a look at the x86, okay, so with x86 machines, it's kind of difficult because you have a virtual memory and memory mapping and stuff like that. But look at the like old machines, 6502 or something, where you just have a memory, right? So, and in a 6502 program, you start a program that is located in the memory, you have the entirety of the memory at your disposal, you have no allocation, deallocation. This is something that you made up to make working with the memory a little bit easier. You see what I'm talking about? It's just like kind of, you created this artificial construct, and now you're dealing with the problems that you introduced by introducing this artificial construct, and it kind of spirals down from there. And I'm not proposing any solution or anything like that. I'm just saying, I'm just stating the reality we have to deal with, right? I'm just stating the reality that we have to deal with. I'm not saying that we have to not use memory allocation or anything like that. It's just like, the reality is that we have to work with these very fuzzy concepts, right? So it's kind of akin to Gödel's incompleteness theorem, if you know what I mean. I don't know if I make any sense, but it's kind of weird. Memory leaks only matter if the code that allocates the memory is called repeatedly. True. Memory leaks only matter if you're poor and don't have any fucking money to buy RAM. Stop being poor. That's how you fucking fix memory leaks. So you fucking fix memory leaks. So she's a rating again. Okay. Just trying to share my experience, and people call me okay. Whatever. Very ungrateful, I gotta say. Very ungrateful. So let me see. So we got the statistics, right? So now we need to build some kind of a table, right? So that would enable us to compress all of this shit. And what's interesting is that we can have, if we have like a lot of text in here, the characters may actually exceed ASCII. So we should probably not work with chars in here, with the sequences of chars. We probably have to work with the sequences of like quote points, right? Maybe sequence of 32-bit integers or something like that. I think that makes sense. So in a table is going to work with 32-bit integers instead of characters, and like majority of them is probably not going to be readable, right? Not going to be human readable. So in here, in this example, we use human readable because the example is small, but we're planning to work with a lot of characters. So the code of the token could be like, you know, few thousands, right? So it could be few thousand. So as far as I know, if you like try to work with OpenAI LLMs, they have some sort of an interface that allows you to show the tokenization of the text, and each token has an ID. And the IDs can be very small or like very big, right? Several thousands of them, maybe tens of thousands. And this is basically the number that is used for that specific token as a result of this BPA algorithm. I think this is my hypothesis. So because of that, I feel like we need to introduce some sort of like, I don't know, tokens. That's a good idea, right? Well, let's call it tokens, and it's going to be a dynamic array of 32-bit integers, right? So it's going to be uint 32 items, size t, count, capacity, right? So this is basically the tokens, and we don't want to operate on this kind of stuff. We want to operate on the level of tokens. What we can do in here, by the way, for the ASCII characters, we can use the code of the token, the idea of the token, as the code of the ASCII character. I think this is a good idea. I think the last time I implemented BPA algorithm in the past, this is exactly what I did, and it was rather convenient. Not sure how well it is going to scale if we start working with Unicode. But anyway, right, so right now we're not working with Unicode. So what we're going to do, so tokens, right? So this is what we have in here. And I suppose what I can do is just like iterate through this entire text and append it into the tokens as ASCII, right? So maybe I might as well just copy paste this entire stuff, right? We're copy pasting this entire stuff. And just a second. And now we're just appending all of these things. So append into le tokens, appending into le tokens. Text I, there we go. And in here we have to work with tokens. Since we're working with tokens, now we don't talk about pairs of characters. Look at that. This is not a pair of characters. This is a pair of tokens, right? So this is going to be something like this, U32T. So this is a completely different thing now. And so here is not the text, but rather tokens count. All right. And in here, tokens items, boom. I don't have to put semicolon here. And that's about it. I don't think I have to modify anything in here. So then we have assorted fracs. So now this stuff is not characters. They are integers and actually unsigned integers. So let's actually put u in here. And I might as well even do something like this, right? So I think this looks good. More or less good. So if I try to rebuild this entire thing, obviously it fails because there's no uint. I'm supposed to include stdint, and here we have some warnings and stuff like that. This is because it's size t. Okay, so let's use size t in here. And here are the pairs. So they're not human readable, right? But that's kind of the point, right? That's kind of the point. So we need to have the table. Right, so we need to have the table that shows the correspondence from a particular code to a pair, So what I'm thinking is that I think the table is going to be an array where index is the number of the token, right? And the element is the pair that points to the two other tokens which represent that pair. I think this is how we're going to represent that. So let me see. We already have pairs, honestly. Right, so here is the pair. We already have that. And in fact, this thing doesn't even have to be array. I don't really know why I made it an array. I could have actually made it AB. I think this is much easier, right? So because the hash table doesn't know the contents of the struct, all it knows is the pointer to this element and its size, and it actually hashes just like a sequence of bytes, right? So the hash table just takes the sequence of bytes that represent the struct and just hashes it. It doesn't care what kind of stuff is in here. I made it array, I don't know, because I copy-pasted some code. For us, it would be easier to actually use A and B, or maybe left and right. So maybe let's call it LR. So let's try to rebuild this entire thing, because I obviously changed the definition, and think it would be easier to, yeah, so we'll need to go and redefine all of these things. Maybe I'm going to do something like that. So this is R. And to be fair, yeah, so yeah, I can actually make it easier. Look at that. Right, so this is just L, and this is just R. Left and right. There we go. That seems to be working. That seems to be working. So now we need to have an array, a dynamic array of such pairs, and dynamic array of such pairs is going to be the table. Right, so let's do something like type def struct pairs, and this is going to be pair items, and then here is going to be size t count, and then capacity. All right. So since all of the ASCII are going to basically represent themselves, I feel like we need to go through the entirety of the ASCII table and just append all of them to themselves, right? So essentially, let's have something like this. So this is a pairs. Maybe I should put all of these global variables that I created into a single place. Or maybe I can put them as local variables, right? So because, yeah. So here's the sort of like tables, arrays, and hashes that we're working with, right? So this is the hash table of frequency. Here's the dynamic array of pairs, which is the table, BPE table. And here is the tokens that we're currently working with. So this entire thing is going to be something like that. Right, so let's keep all of that in a single place. And the pairs, right, so the first 255 elements are going to be like so. Zeroth element, I suppose, is going to point to, it has to be a pair, right? So we need to understand what we're going to be considered the leaf pair, the pair that basically represents the final element in there. So I think the way I did that is that I basically set the left to itself, right? So we set the left to itself, and R stays undefined, right? So it doesn't really matter what is in there. If you have the left element of the pair equal to the itself, to the index, that means you've reached the final token, and that's the character that you care about, and R doesn't matter. And we kind of need to repeat that 255 times, right? So we have to repeat that 255 times up until 255 in here. So after 255, we're going to be inserting new elements in here for new pairs, for composite pairs, I would even say. Right. And those new pairs are going to refer to things like 69 and 120 or whatever, right? So essentially what you're supposed to do, you look at the left pair, okay, 69, then you go into 69 somewhere in that specific pair, like so, right? And then you realize, oh, okay, so 69 is the final element in here, so, and this is how I know that 256 is a pair of 69 and 120. Right, so this is basically the table that we're trying to build in here. But first we need to initialize this table with this kind of stuff. Obviously not all of the characters from 0 to 255 are displayable ASCII characters, but it doesn't matter, right? So I just want to initialize it with something, so all of the characters, all of the codes from 0 to 155 are sort of like reserved as leaf codes. Hopefully that makes sense. Hopefully that makes sense. So let's iterate through, I suppose, you insert it at t, 0 up until 256, right? And we're going to be basically inserting all of that stuff. So I think I want to put this thing in here. So di append pairs, and we are inserting pair where the left element is equal to itself. We can even maybe even do it like that. So that's basically the initialization I'm talking about. That's basically the initialization. So initialize the pairs, then we're preparing the tokens, and so on and so forth. That's pretty cool. That's pretty cool. That's pretty cool. So yeah, let me see if this entire thing builds and okay, so it does compile. So essentially what we have to do, we don't really have to sort this entire thing. I sorted it so I can display the top 10. What we have to do, we have to find the maximum. Right, so and the maximum can be found linearly. The problem with Q-sort in here is that it's O log n log n, right? So n log n. But I can find the maximum in linear time, which is better than this. So I'm probably gonna remove this entire stuff, but it's just nice to have to be able to just sort them and see how they look like. So maybe I should not remove that because it's kind of useful. Right, it's kind of useful. So none of that code is really needed, but it's very convenient for displaying. So maybe what I'm gonna do is, I don't know, display sorted rex or whatever. I'm just gonna keep it in here. So let's actually go ahead and find something like max frac. Max frac. We can try to do something like this. So it's gonna be 0. So max frac. It's going to be an index of max frac. Max frac index. Right. So we're going to iterate starting from, I suppose, 1. Right. So because we already consider 0 to be the maximum. And we are iterating HM length. So this is what we're iterating in here. Right. So this is what we're iterating. HM length returns pointer diff. So maybe because of that, just to be safe, it's better to keep it as pointer diff like this. And we're going to be doing something like that. Okay. So now, if frac I value is greater than frac max frac index, okay, the word frac in here is repeated twice, which is kind of dumb. So let's do something like this. So this is a max index. So if it is bigger, what we do is we assign the new max index to this. And there we go, we found the maximum frequency in here. Right, we can even print this entire thing. So how do we print those things? So this is the way we print it. So this becomes frac. I think it's not really called frac. It's called actually frax, isn't it? Yeah, it's called frac apparently. Why did I call it frac? Am I stupid? Maybe I am stupid. But anyways, that's besides the point. My stupidity is kind of besides the point of what I'm doing. So, okay. So it has to be, so what you don't like, this is, I forgot the value. I forgot the value. So what else do we have in here? It is not a pointer. Can you see Scheisse that I'm doing? Yeah, you should be able to now see the Scheisse that I'm doing. I'm going to replace the arrow with a dot. What the fuck has happened, Brovsky? Yeah. Boom. Okay, so this is the maximum pair. This is the maximum pair. So the thing we have to do now is that we need to append this pair into our pair list. Right, so we need to append it into our pair list. And I think what we can do is just like literally just append it, right? So just simply append this thing. Simply append this thing. Let's fucking go. So it's gonna be di append pairs frac max index. Yeah, but it's not even that, it has to be the key, right? So because we're appending the key, and there we go, we just created a new token specifically for that most frequent pair. So this is kind of cool, actually. This is kind of cool. So after that, we have to iterate the tokens again. And compress. So we need to find every time this pair occurs and replace that pair with the new index. That's what we have to do. So let's fucking go. because of that, we need to like have a second tokens array. Right, so this is where we store the original sequence of tokens that we analyze. And then we need to have a token array, which is like basically the output. And then we'll have to swap them out, but that's going to be a separate issue. So tokens out. Let's just call it tokens out, like this. Tokens out, tokens in. Maybe we should call this thing tokens in as well. I can just select this entire thing. Tokens in. Yeah. I think that's a good one, right? So we have a tokens in, and this one is a tokens out. So this is where we're going to do the compression. Okay. Now, what I'm iterating tokens in. Size t, tokens in, count, plus I. Here we go. And I'm actually iterating it with -1, right? So that's what I'm doing. I'm iterating it with -1. I have to be careful that this entire thing is not equal to 0. Yeah, so this is, yeah, it's a little bit annoying, but, and by the way, this one has to be with -1s because we're not iterating pairs in here. I copy-pasted code and did a very dangerous thing. Yeah, so we iterating specific elements because we appending them into the tokens, right? So there should be no -1 here, but here we should have a -1 and it's still unsigned. Okay, I guess I can't win this kind of situation. Whatever. Okay, so we're iterating the pairs in here, and so what do we do? What do we do? We need to construct a pair the same way we did it in here. So we are just constructing the pair, and if that specific pair is equal to the most frequent pair, we have to replace it with an index. So how are we going to be replacing? So we're basically going to iterate the input tokens and append them into the output tokens, right? And if we encounter the frequent pair, we just replace it. So that's how we're going to go about that. So here's the pair, right? So here's the pair. I need to compare it into the most frequent pair. The most frequent pair is actually this. Right, so can I just do something like, I don't know, memcp cmp? I think I can do that. I can, in C, you can literally compare 2 chunks of memory. And I think it's a good operation that we need in here. So I'm comparing pair and the most frequent pair. Like so. And obviously you need to provide the size of this entire thing, and the size of this entire stuff is the pair. Might as well just say pair. There we go. So, and the types of this, of the key must be a pair, right? Is it pair? Yeah, it is pair. So if these 2 chunks of memory are equal, this is going to be equal to 0. So if they're equal, that means we found the most frequent pair. We just found it. Because of that, what we have to do, we have to append into the tokens out, into the output tokens, the index of that pair, and the index of that pair, if I'm not mistaken, I think is just like the last index, so it's going to be pairs count -1. All right. If it is not the most frequent pair, what we append into the tokens out, actually, what we append in the token out is just the left items in here, like this, which creates an interesting problem, I think. It does in fact create a very interesting problem. It's when, all right, so you have A, B, C, D, E, and for instance, DE is the most frequent pair, right? So in the output, you did A, B, C, and then you replace it with X, right? And that means you have to skip it. What I'm thinking is we have to iterate the entirety of the input tokens, and we have to vary this step with which we are iterating. We must vary the step with which we are iterating. We have to check, I think, if I plus 1 is greater or equal. So essentially, we are looking at the last character. If it's that, what we simply do is this, right? We just like append that current thing and forget about it. Otherwise, we have the next character. And in that situation, we can create a pair and we can compare that that's the pair we're talking about. All right, so we then insert the new pair into the tokens out, and we have to kind of increment this entire thing by 2 to skip both of the tokens that we just replaced. So in this case, we have to skip by 1. In this case, we skip by 2. And in this case, we also skip by 1. This is, I feel like, what we have to do. That's what I feel like we have to do. It's just like we have to vary the step depending on the situation of how we replace this entire stuff. And now, I suppose tokens is just like, yeah, basically convert. So we took the most frequent pair and we replaced it with a special character. So let me try to build this entire thing and we can try to visualize the entire process. Okay, so here's the pair, pair C. Okay, so and that seems to be working. So you know what I want to do? I want to have some sort of a function that takes tokens and basically prints them as text. Let me show you what I mean. Render tokens. I'm going to call it render tokens. And it's going to accept the tokens. And what is it going to do? We also probably need pairs, by the way. We probably need pairs. I'm going to put it in here. We are iterating the tokens. We are iterating the tokens. So here's the tokens, count plus I. So, first of all, we need to assert that tokens items I is less than we have pairs, right? So this is very important. Otherwise, we're going to basically have buffer overflow. Then we are looking at the pair at this specific index. And if L is equal to the token itself, right? And as you can see, we are repeating this hairy expression too many times. So let's actually call it just token. You insert it to token. There we go. So token is less than that. And if this entire thing is equal to the token itself, we reached the leaf token. In that case, I think we can just print it as a character. Let's just print it as a character like so. If it is not, let's print it, let's just highlight it as the token that we just replaced, right? So I want it to scream, I'm a token. So let's print it as a number, and also wrap it in, you know, brackets, so we can literally see what's the new token that we just created. And this is going to be a number like that. And then I'm going to also print a new line in here. So this is the function that I want to have. Okay, so it doesn't really work. Pairs count, pair, yeah. So this is actually pair C. There's several of them. Okay, so this is items. Okay, very cool. So what I want to do now, I want to render both tokens in, the original text, and tokens out, the text with a compressed most frequent pair. I just want to print them and just like compare them. Did we actually replace the pair and or not? So I'm going to do render text, render tokens, and I'm going to do tokens in, also with pairs. Right, so this is pairs. So this is the original text. Build PPE. Okay, Emacs. Fuck you, Emacs. Okay, so Emacs doesn't like long outputs, right? So, and as you can see, it printed everything correctly, right? So there's no additional tokens in here or anything like that. Now let's print tokens out. So in tokens out, the most frequent pair will be screaming with brackets. Okay, look at that. So replace. That's very interesting. Replacing. Okay, the most frequent pair is space T. Right, the most frequent pair is space T. So if I search space T, all right, look at that, a space small t. This is the most frequent pair, and in all of these places, that pair got replaced with the token 256. Right, it got replaced with the token 256. We can also print the size before replacing. Right, so this is the old size, token in count, and this is the new size. There we go. So we went from 513 tokens to 498 tokens. Right, this is basically what happened. What we have to do now to implement the, the compression algorithm is to take this output and feed it back into the process. We have to keep repeating until we can't compress it anymore. And we can't compress it anymore when the most frequent token has a count equal to 1. As soon as you have this situation, you can't really compress it anymore. And you've got a table which you can then use as a grammar to generate more text and stuff like that. So that's basically it. So this is what LLMs use, but obviously it's not exactly that. They say that it's slightly modified. I don't know how much it's modified. Maybe it's just like tailored towards the specific infrastructure or maybe specific algorithm and stuff like that. But the idea maybe is there. Yeah, we also need to do a double buffer. Basically what we need to do now, we need to swap this entire thing. Right, we need to swap in and out and just continue doing this entire thing. All right, so let me think how we can approach this entire stuff. So do we in Knob have something like swap? Do we have swap? We don't even have swap. Yeah, damn it. Knob, something like Knob swap would have been pretty cool. But in all honesty, I don't know. Maybe it not. Would be not. Because you need some sort of like a temporary buffer or whatnot. We can implement maybe DA swap, which takes like a and B, DADB, right? And essentially what we have to swap in here, we need to swap the contents of these two things, right? So should be relatively straightforward. Usually they have but what if your dynamic arrays have more fields in here? Well, that's going to be up to you then to swap it properly. I'm just not sure if this is a good idea to have a macro like that. I'm actually just not sure. Is there a mem swap, really? No, there is no such thing. I don't see it at least. You're debating me. Chat! Stop debating me. Stop. Oh, it's a suggestion. Well, I mean, that means I have to implement it somewhere or whatever. Don't want to implement Scheisse, bruv. Don't want to implement Scheisse. I mean, I can just assign it. What the fuck am I saying? So essentially, after all of this thing, I can do maybe something like tokens T, tokens in. Since I saved tokens in, I can quite easily replace them with tokens out, right? And now I can, I could do something like that. And I mean, who said I can't turn it into a swap thingy, right? So I can do swap. So you accept the type and then X and Y. And in here, yeah, well, why didn't I think that I can just provide the type? I don't know, don't like providing types. So this is a temporary one, we save X, we can replace X with Y, then we put it like that. And obviously we want to actually put parentheses around all of this because we don't know what is exactly the sequence of tokens we get from the parameters in here. Also, what the fuck is that? Right. And also we have to escape this kind of thing, and there we go, while 0. Yeah, so this is basically what I want to do. Maybe I should put that into Knob, but I'm not quite sure. Anyways, so this is gonna be le swap, tokens in, tokens out. We just swap them, and we just need to repeat the entire process. So here we're just initializing pairs, here we initializing tokens in, and this is where we're doing the compression. So that means in here, this is where we gotta do the loop, right? So this is where we're gonna do the loop. Compression, finding the maximum, printing the maximum. I'm not sure if we care about printing the maximum, adding a new token, generating token out, swapping it out. Right, so, but here's the thing, in token out now we have a previous garbage. So I think before constructing token out, we have to clean it up. Yeah, so this is what I think we need to do. We need to do count 0, right? Because on the next iteration is going to be dirty, so we need to clean it up first. And that's basically the algorithm. And we have to do that up until the most frequent one becomes 1. So this is where we actually do that. So if this value, if the count of the most frequent one is equal to 1, or let's actually do less or equal than 1, this is basically break. We're breaking out of this entire algorithm, right? So compression is done. Compression is done. And we don't continue this entire step. So what I'm thinking is that what we can do is print, like render the sequence on each iteration, right? So we render the tokens. So this is the tokens in up until it, you know, can be rendered no more. Let's fucking go. So it didn't work. Render tokens, you have to provide the pair to be able to render that token. So it's called pairs. Okay, so swap tokens. You didn't like something. I don't know what exactly. Provide. You have to provide it. I'm sorry. So this is the tokens. Le tokens. Oh shit, Brovsky. That's a lot. But I mean, it's kind of going somewhere. But I think what we need to print instead is the size. Okay, so we got some subs and some beats. So thank you so much, Selin Heli, Freakier Noriat, J2 Remy. So thank you. Armageddonium, thank you so much for 100 bits with a message. Hi Tsoding, I have a question for you. Have you ever worked with graph drawing algorithms? No, not really. Specifically planar drawing graphs. No, I've never worked with that. So let's actually Google it up. Planar drawing graphs. Is there any? Okay, planar graph. Okay, a planar graph is a graph that can be embedded in a plane. So it's sort of like a geometrical theory of graphs. So because quite often in a graph theory, people look at the graph without their geometrical representation, right? So it doesn't matter whether the edges are cross each other or whatnot. Okay, this one is, okay, this is a very interesting area. Okay. I'm looking for ways to implement a graph drawing algorithm that can fit rectangular boxes with edge labels ideally. I looked through force-directed algos, they are shit. I found one algo that is good enough, but it draws vertices as dots, not boxes. If you know anything about the topic, help would be pretty much appreciated. I don't know anything about this topic, so that's the problem. I never done that, but you just give me a pretty cool idea for a topic for a stream. So yeah, like I never tried to do that. I just realized, like, why didn't I try to do that ever? Because that sounds like a pretty cool idea, honestly. Yeah, and then you try to kind of feed it. Damn, that sounds like an interesting thing to try to code. Yeah, I'm so sorry. Like, I don't know anything about it, but I will consider doing a stream on that. So thank you so much. Maybe I would look into how graph viz work, because I think graph viz deals with similar problems because it's literally an application for rendering algorithm, but I don't know the state of their code base. Maybe you can't really extract anything useful out of that. Right, so yeah, maybe you can get some interesting information out of their code. So yeah, sorry, but thank you. So Kafka Führer, thank you so much for Twitch Prime, and Never Normal, thank you so much for Twitch Prime with the message. Thanks for your streams. I watch the recording almost every evening. Thank you for watching them. Right. So the Land of Lisp had an exercise about graph viz. That's very interesting. It's pretty cool. Never read it actually. Okay. So yeah, it takes too much time to render it. Maybe this is because the Emacs is a very slow terminal. So let's actually try to render the sizes of the tokens and see if the size slowly increases. Okay, this is not what I wanted. Fuck Emacs. I hate Emacs. When you start outputting in a single line and you forget new line, it literally locks this entire shit fucking editor. Okay, so let's fucking kill it. It's just like, it's so easy to fucking kill it. Okay, alright. It's a shit terminal. It's a very fucking shit terminal. So is that a prob? I don't remember. Is it in prob? Is it in sodding? I think it isn't. Okay, so here it is. I just forgot a new line, and there you go. You're dead. You're basically fucking dead. So just kill Emacs, right? One mistake and you've mistaken. No, but let's fucking go. So what the fuck are you saying? So this is gonna be count. Okay. what else do we have? Cool. So now I can try to do BPE. All right, and it compressed it to 1. Holy shit. How did that fucking happen, bro? That doesn't make any sense. We did a fucky wacky somewhere. Like, how did it compress the entire thing into just 1? Because the count in here... Oh, I think I know why. I have to clean up the goddamn frequencies. I forgot about this entire shit. Yeah. All right, let's quickly try to do that. So where do we start working with the frequencies? Here's where we start to work with it. STBDS, HM clear, reset. Free. I don't want to free it. Do you have? You really don't have clear, clean, reset. There's a str reset, but there's no reset of the hash. Clean, bro. I don't want to free it on. Bro, this sucks. This hash table sucks ass. Like, if you can't clean it up, like, what's the use of it then? I don't want to free it. Freeze the hash map and say, bro, that fucking sucks. Anyway, so can I do HM free on at least at the beginning? Damn, not having a reset operation for hash map fucking sucks, I'm telling you. All right, so it actually went down to 208 and couldn't compress it no more. Right, it literally couldn't compress it no more. All right, that's very interesting. So let's now try to print the sequence of tokens, because I want to see how the text like shrinks over time. I think it's going to be interesting. So I hope it's not going to be too bad. All right. And at some point, yeah, so at some point, this is basically how it shrunk. So we have almost no ASCII characters in here. We have almost no ASCII characters, so it's completely compressed as much as possible. And it created a lot of tokens, actually. So how many tokens we managed to create? Let's quickly print that. Generated, so Z tokens. So it's going to be pairs count. So this is how many tokens we now have. 349 tokens. I'm not sure if the encoding is readable. Let me quickly remove that. Okay, so 349 tokens. We started with 256, right? We started with 256. Now we have 349. Right. So, and most importantly, we have now a table, right? So pairs is a table where each entry points to 2 other entries, or the leaf entries point to themselves. So this is sort of like a directed graph. I wonder, speaking of GraphViz, can we visualize this entire shit with GraphViz? So generate graph, like a dot, it's called dot, and I'm going to provide just pairs. So this is going to be generate dot, and let's create it as a function. So this is going to be void pair pairs. So this is pairs. All right, so this is something like that. And what we need to do, we need to just iterate through all these things. So this is going to be size t. In fact, this is basically token, right? Token less pairs count. And essentially what we have to print in here, we have to print ZU to, I think it's just like this. From token to pairs items token left. So this is the left one, and then the right one. And don't forget the new line. Don't fucking forget the new line. So after this entire shit, it didn't even fucking compile because it's a token. Okay, cool. It generated, but there's still some warnings in here. Because it's a U. Okay, so let's actually make it something like U32T, and this entire stuff becomes just U. Are you happy now? You are in fact happy now. Look at that. So this is basically okay, so here's an interesting thing. So some of them are leaf things. So what we have to do, we have to check if token is equal to the left one. That means it's a leaf, right? And we shouldn't print it. So because of that, we probably should do something like this. If it's not equal to that, only then print it. All right, so that makes sense. That actually makes a lot of sense. 250. Okay, yeah, okay, so it refers back to these things. It refers back to these things, but things themselves are not printed because they're leaves, essentially. Because they're essentially leaves. And can we just now make it a dgraph? If I remember correctly, it's something like dgraph pairs, like this. I don't remember if you put like semicolon in here or not. I hope we're not gonna spend 3 hours debugging because of a single missing semicolon. Right, so this is roughly what we want to have in here. I think we forgot the new line. Why I keep forgetting the new line these days? I don't quite understand. We don't really print anything else. Okay, we can do. Is that the correct dot format? I don't know, honestly. I don't really know. So here's the pair and a pair dot. Okay, at least my Emacs highlights this entire shit. So do I have dot? I don't. Let's install GraphViz. Let's fucking go. XBPS query rs GraphViz. All right. Let's fucking install that scheiße, meine Freunde. Let's fucking go. Thank you. All right. So here's the GraphViz, and yeah, I can try to maybe even open this entire thing and compile it and. All right, so I actually guessed this entire shit. Holy fuck. LLVM documentation, let's fucking go. Let's fucking go, LLVM documentation, love it. But yeah, so this is basically the graph. This is basically the graph that we got, that we kind of generated out of this text. I love reading docs. I love reading docs. A classic dot unreadable tree. Yeah. Fucking classic, mate. Fucking classic. So yeah, that's how you generate this entire thing. It would be kind of cool to have like a way to dump the pairs into hard drive and then maybe load them up later to generate some text and whatnot. I think that would have been super useful. How can we do that? We can just take these pairs and simply dump them as binary. So that's one thing we can do. There's a little bit of a waste on the 256 first things, but I don't think it's that big of a deal, right? So yeah, let's actually try to do that. Maybe something like dump pairs. We're gonna accept the pairs. And maybe also file path. So as far as I know, in knob, we have a function write entire file, which just basically takes a buffer and dumps the entirety of that buffer into the file system. So we can do file path. So pairs items. So this is basically the pointer to the data. And then we need to provide the size in bytes, right? So we can provide pairs count, but this is a size in elements. So we have to multiply it by the size of a single element, size of items like this. And obviously it may return an error, right? So, and I think this is what we can do in here. So we just like return an error in here. Okay. So after that, we can do something like this. So dump pairs. Pairs bin, and obviously if it fails we're gonna return 1 in here. Yep, let's just do something like that. Did it create pair? It didn't, motherfucker. I forgot to rebuild. Just a second. All right, so there you go. Here's the bin, and here is basically the dumped memory, right? So yeah, majority of these things are just zeros, and then at the bottom we have some other stuffs. Here's the hexel editor. Yeah, you can clearly see here's the left, here's the right, and because the numbers are to the left, this is a little engine. Okay, so that makes sense. That makes a lot of sense. So we just dump this entire memory. Who needs JSONs and YAMLs and some other shit? You can just dump memory. You just can dump memory directly. All right, so thank you so much, Armageddonium, for 100 bits. I already forgot how to read your name, I'm sorry. Thanks for the feedback. As a graph drawing, I don't recommend GraphWiz. It's total shit. And Plantum and Plantumal, that is based on it. Plantumal is good, but the layout just sucks. I never heard about it, actually. I don't really render graphs that very often. PlantUML, okay, so that's very interesting. So they had a versatile tool for that facilitates the rapid and straightforward creation of a wide array of diagrams. UML. No? What the fuck? That is a straight up no for me. I will refuse use this software purely for that. So thank you so much. As based on it, this is why I'm working on replacement for my specific use case, but planning to expand it. If you're planning to dive into it, I recommend algos from Mervan, Turboplane. Okay, that's what I'm doing for now. Okay, so let me see. So there are people who literally study, like, you know, research how to do this kind of stuff. Huh. And it's even part of Boost. God fucking damn it. Boost must have literally fucking everything. Like, why? Why does it have to do literally fucking everything? But anyway, thank you so much. Noted, I'll look into these things. So thank you for another 100 bits with a message. If you're planning to use GraphWiz layout, I suggest using Nito layout engine. It's just gonna look a little better, although generation is slower. Okay, I'll give it a try. So let me see how do I even do that? So maybe it's part of the dot. Is there just dot? Okay. So engine. Okay. Nito. Damn, this is absolutely useless, bro. Ah, it's okay. It's a wrong thing. Do you have help? Nito. Okay. So engine. Set layout engine to V. So I have to do something like that. Okay. All right. So here's this stuff, and I'm gonna open it. I suppose I have to do something like Nito. All right. It didn't help, but I see where you're coming from. I see where you're coming from. If this entire stuff was a little bit less complex, maybe it would make sense. Okay, that's pretty cool. Pretty cool. Thank you. So, and thank you, Anonymous Gifter, for gifting this up. So yeah, we tried. We tried. That's pretty cool. All right. So we dumped pairs. And yeah, so maybe we need to have a way to restore the pairs somehow. There was an attempt, yeah, exactly. We can have some sort of operation that loads the pairs, right? So load pairs. So this is going to be Boolean. We're going to do something like that, file path, and also going to take a pointer to the pairs. Because it might be a quite heavy operation to load the pairs back. So to recompute the pairs, right? So because we don't want to recompute them over and over again, we're going to be probably working with a bigger text, right? So much bigger text, and I want to be able to just like compute the table once, dump it into the memory, and then load it later, so I don't have to recompute it over and over again. So I can experiment with this implicit grammar that we discovered. So Sodin is dumping pairs every now. Okay. This is literally the reason why I'm trying to ignore the chat. It's just like it's like honestly, streaming is a schizophrenia simulator, right? So you're trying to do some job, and there is this like a voice, like invasive voice that's trying to constantly distract you. It's a literal schizophrenia simulator. Anyways. So what we need to do in here, we need to first load the entire file. So we have an opposite operation in Knob. Write the entire file, and we have read the entire file. So let me do that. So knob.h, read the entire file. So here it is. So it actually accepts the buffer into which is going to read all of that. So we can actually maybe pre-allocate it in here. So I'm gonna, this is not, I have a shortcut for small break and it's called SB and it just got triggered. Freaking classic, freaking classic. Okay, so I'm gonna give it in here. So this is the file path, and obviously it may fail, right? It may fail, so we're gonna actually return false in this specific case. And I'm thinking maybe I should accept this entire stuff so it's none of the function business to do the memory management. I think that's a good idea. All right, so after that, we need to take the size of the buffer, right? And we need to make sure that it is divisible by the size of the pair elements. Right, so this is going to be pairs, items. Yeah, so it is divisible. We're going to do an assert, right? Let's actually not do assert. If it's not equal to 0, we probably need to fail with an error, std error, unexpected size of s should must be divisible by 0. Right, and what should be divisible by? It should be divisible by that. Right, and we can also print the size of this entire thing. So size of the file path, which is SB count, should be divisible by the size of the element. That's very important. Otherwise, it's just like not gonna align properly. And we return false in here. So after that, what we can do, we can actually do something like this. So this is items, SB items, right? So we take a pointer to the characters, pointer to the buffer, and we cast it to the pointer of the pairs, right? And now we also need to have maybe items count in here, and it's going to be this thing divided by the size of the element, and this is precisely the reason why it has to be divisible, right? This is precisely the reason. So after that, we can quite easily just iterate all of these items count, like so, and just keep appending them into the pairs. Right, so this is going to be the pairs. It's already a pointer, and what we're doing in here is items I. There we go. So, and after that, if it succeeds, we return true. Right, so we're just like reading up bytes. We make sure that the amount of bytes makes sense. It's divisible by the amount of elements that we have, and we're just reinterpreting it as an array of these pairs, and we pushing them back into the dynamic array. So that's essentially what we're doing here. In fact, we didn't even have to do that, honestly. I just got an idea. I just got a pretty epic idea, honestly. What if we do like this? We own the allocation of this buffer. Okay, let's own the allocation of the buffer. And then we're gonna actually reassign, we could reassign the whole thing. Now, let's not do that. So the cool side effect of this specific approach is that if you already have some pairs in here, it is going to append more pairs in here. So you can have two files and you can quite easily concatenate them. Right, so you can actually quite easily concatenate them. Right. So yeah, so that will allow us to, you know, save all of that quite easily, which is pretty cool. So what we can do, let's actually test all of that stuff. Maybe we need to create a separate, let's create a separate utility that loads the pairs and generates dot thing. Okay, so yeah, let's fucking go. I think it's a cool idea. So we can move this dot generation algorithm to a separate utility. Yeah, that's kind of cool. So we'll go here, and what we're going to be doing in here is maybe, let's call this utility something like bpe to dot. That's a pretty good name. I really like that. bpe to dot.c. Okay, so here's that. So bpe to dot. So now we're starting to kind of repeat a little bit of a code. Maybe we could factor out this entire thing to something separate in here. For example, build tool. So here we have maybe src path, and in here we have bean path, something like this. And now we can quite easily just put it like that. Obviously, it probably needs to accept the pointer to cmd because it's going to be using cmd. So in here, we have bean path, and this is src path, like so, src and bin, and then we just run this entire stuff synchronously, run it synchronously, and there you go. So after that, what that means, I can do build tool, build folder, bpe, bpec, and return one. So now we can do bpe to tool. So let's fucking go. JSON to bpe. We've got some more subs. Thank you so much. Thank you so much, Coffee Before Code, for TML subscription, and Iceleo, thank you so much for gifting sub. Thank you, thank you, thank you. All right, that's pretty cool. Okay, so now it now becomes quite easy to just, like, you know, add a new tool in here, like building a new tool. Look at this neat code. Look at this neat code. I'm gonna just do nope this, and obviously it doesn't build because it's not a pointer. What else do we have in here? So we didn't like something in here. Build folder. You didn't like build. This is because I have to put pointer to the CMD. That makes sense. Okay, so now it is working. It is working. That is absolutely fucking bizarre. Wait. I've never seen this error before. What the fuck is going on? Excuse me. So this is what we're trying to build in here. Oh my god. I have it saved in here. Everyone calm down. I have it in my buffer. Emacs saves the day. Absolute coding. Absolute fucking coding. Yep. I'm actually not sure. I think I'm gonna like swap them around like this. Yeah, let's fucking go. And knob. Oh, right. So this one has to be a pointer. A pointer. This one has to be a pointer. All right. Another a pointer. Another a pointer. Another a pointer. Thank you so much, C, for making me freaking replace all these stupid ass dots and shit. I'm so goddamn fucking tired. Okay, that was the last one. All right, so we're Gucci. We are in fact a Tamaguchi. All right. Okay, so BP to that. Alrighty. No such BP to. I'm an idiot. I'm an idiot. Yeah, I wanted to do dot. I think I'm already a little bit tired, chat. That's fine. That's fine. We're gonna get there. Don't worry about it. And define reference domain. Okay, that makes sense. BP to dot. I'm gonna include this kind of stuff. Ayo, ayo. Ayo, I'm not fucking you. And I'm gonna just return 0. So what I'm thinking is that we need to have command line arguments, right? So this is gonna be char, argv, whatever. And in here we need to start parsing things. So I'm gonna have something like a program name. I'm gonna shift argv, argc, but shift is implemented in nub. So what we have to do, we have to bring this thing in here. Boom. All right, so here's the shift, and we need to check argc is less or equal than 0. That means you didn't provide the input. You must provide the input, bruv, you must provide the input. So let's actually tell that. Right, no input is provided. We can even freaking tell the usage, right? So the usage is the program name, input, bin, right? So don't forget the new line. Don't forget the new line. Program name. There we go. And here we're gonna exit with non-zero exit code. So after that, we have the file path, which will also shift argv. So the next thing we have to do now, we have to just read that file path. So let's get the code that is responsible for loading the pairs. We're gonna put it in here. So here's the loading the pairs. Cool. But we need the definitions of such things as pairs. And we need to share that definition between both of the tools. What that means, the time has come. Why FPS of the camera is down? The time has come for a common module, right? So let's maybe create something like bpe.h, and it's going to be header where we're going to share like the definitions and stuff like that. So let's put the inclusion guards, right? So this is the inclusion guards. We're going to define that, and I'm going to do end if. There we go. And where is the definition of the pair? So here's the pair, and also the pairs. All right, so this is the definitions that we need in here. Do we need anything else? I don't think so. I think that's enough for now. As we need to share more and more things, we're going to be moving them into the bpe.h. Okay, so now if I try to compile both of these things, yeah, it obviously fails because it doesn't know what is a pair. Let's include bpe.h, including bpe.h. Okay, so we also need to have pairs, but this is bpe to dot, so we need to include bpe.h in here as well. All right, so you inserted 2, that's understandable. So that means we probably have to do stdint.h in here. Cool. So file path, okay, that's pretty cool. So now we're freaking ready to do this thing. So load the pairs, load the mother flipping pairs, provide the file path. Let's put the pairs somewhere here. Pairs 0, and also string builder sb like that. Boom. Let's fucking go. If not, return 1. And we loaded the pairs. So once we loaded the pairs, now we can try to generate the dot. So we can move this whole thing there. And I'm thinking, do we just output that to standard output, or do we also accept the the output in here? We can do something like output dot. We can do that actually. Who said we can't do that? So let's call the file path input file path. So we got that. Then we can do something like this and say no output. Output is provided. So this is the output file path. Something like this. That's pretty cool. So we load in the pairs, and now we're ready to generate this stuff. What we can do, we can just open the file and just write into there, or we can kind of render dot. So essentially the input is going to be pairs, and output is going to be the string builder into which we're rendering this entire shit. So instead of printfs in here, we're going to be doing sb append sister. So we're appending chunks of strings into that sb. So we're rendering that into a single buffer. That's what we're doing in here. We're rendering all that stuff. So there'll be a little bit of a problem in here with printf, but we can also always use tmp as printf, right? So, and then simply append sister to sb in here. We can easily do something like this. And the same goes for this thing, sister sb, right? So we're rendering the dot, which makes it then super easy to dump the entire buffer back into the file system. So, and what's funny is that we can reuse the string builder, the same string builder that we used to load the pairs, right? So we kind of need to clean it up first, and we can now reuse it. And the memory that was allocated during loading the pairs is going to be reused for now rendering the dot. So that's actually kind of cool, honestly. That's actually kind of cool. So then we're just render the dot. Look at that. Render the dot. We provide the b, and then we provide the pointer in here like this. I think load the pairs also accepts it as a pointer. Yeah, it also accepts it as a pointer, so it has to be like that. And after that, we can finally just, dump it into the file system. Just a second. Nope.h. Write entire file like this. So this is going to be the output file path. The data is sb items, and the size is sb count. And obviously it can fail. If it fails, return 1. All right. So we can also say something in here, maybe like info generated as output file path. Yeah, look at that. This is actually kind of cool. This is actually kind of cool. So we're not like constantly reading, writing into file. We read once, generate this entire thing into the memory, and just write it once. So that's basically what we're doing here. Okay, so let's fucking go. So it doesn't compile properly, obviously, because, well, I mean, we probably don't have to do that anymore. Okay, so pairs, it probably needs it as a pointer. Okay, and that seems to be working. That seems to be working. Cool. So if I try to run BPE2 dot, it asks for an input. So the input is going to be pair bin. Okay, so we get the pair bin. And then I'm going to say pair dot. Right, so here's the pair dot. And it worked. If we take a look at this entire thing, okay, that seems to be working. All right. So let's try to work on a simpler text. Right, so here we have a pretty, you know, big text. What if I say that the text is actually something like, you know, the quick brown fox, right? The quick brown fox jumps jumps over the lazy dog. Right, so let's do something simpler. I'm gonna try to rebuild the whole thing. We should probably accept the text as input parameter, but in the future we'll probably have to accept it as a file, right? So we have to read the text from the file, do the BPE compression and dump it into the binary. So with the other tool we can now inspect it and build the graph and stuff like that. Right, so BPE, just do the BPE. Okay, so that should have generated a new pair in here. It didn't really print anything, unfortunately, but whatever. So BPE2 dot pairs bin. All right. Well, we have to do pairs dot. Yeah, is that a good one? Yeah, I think it's fine. So in here, it's much smaller actually, surprisingly. It only added. Yeah, the problem with the quick brown fox jumps over the lazy dog is that it. Yeah, there's no that many repeating pairs. Yeah, there's not that many repeating pairs. And okay, so Nito. But I think at least it's gonna look good, right? So at least it's going to look, yeah, that's basically what we got. So we managed to find only like 2 pairs, right? So the first pair, it refers to characters 101 and 104. And another pair refers to 256 and directly to the space. There's not that many repeating pairs, unfortunately. So yeah. So, but yeah, so we have some tool that allows us to generate the text and then create a binary file and then turn it into the dot file or whatnot. I'm already streaming for 2 hours, actually. I'm already streaming for 2 hours. So I achieved what I wanted to achieve today, implement the compression algorithm for the text. The compression algorithm. So on the next episode, tomorrow probably, we're gonna try to. So do we need to implement the tokenizer? Honestly, to actually generate random text, I don't think we need to have a tokenizer. Let's tomorrow try to generate random text out of this entire thing, right? So I'm going to prepare the huge body of text, right? So the logs from our Discord channel and stuff like that. We're going to tokenize it, we're going to compress it, we're going to get this implicit grammar, and we're going to try to maybe generate some schizorant out of that. So sounds good, sounds Gucci, Tamaguchi, as usual. So yeah, that's it for today. Thanks everyone who's watching right now. Really appreciate that. Have a good one, and I see you all on the next recreation programming session with Ahu, Mr. Azuis, and I love you all. Mwah. Alright, this is the footnote of the session, and I would like to quickly implement something. So we got 2 tools. The first one converts text to BPE. I renamed it to text to BPE because it makes more sense. And I make it accept the text as a path to a file, right, and it also accepts the output path, right? So before it was actually hard-coded in the source code, and it's not particularly convenient, so now it accepts it as a command line. And the second utility, it converts BPE table to dot format, so then you can render it with GraphViz. I'm not sure how useful this thing is, because if BPE table is sufficiently complicated, you can't really make sense out of the graph anyway, so it's kind of useless, so maybe I'm going to remove it. So let's actually try to test these tools, right? So I put the Wikipedia paragraph into a separate file so I can use it in here. And now let's actually do txt to BPE. I'm going to provide the the paragraph in here, and then the output is going to be with the same name but with the extension BPE. Right, so it's kind of cool, but you can't really see what is going on in here, right, unless you use dot, but it's useless. So what I was thinking is that we need some sort of a tool that actually renders the tables of the tokens, right? So I want to see the ID of the token and the text of that specific token. So let's quickly implement that utility. Let's call it something like bp-inspect, inspect.c. Right, so in here, I suppose we need to include all of the other things that I usually include, specifically stdio, knob, and the common bpe.h. So for the main, I think we'll need to parse command line arguments, so I'm going to put it in here. And for the usage, I'm gonna also use the same format of the function. Right, you see how easy it is to program? You just copy paste code. You don't even need LLMs, bro. You don't even need LLMs. LLMs are for people with a skill issue who don't know how to fucking copy paste. I'm telling you. I'm fucking telling you. That's it. I don't even have to modify much, right? So that's basically the skeleton of the utility bp-inspect. Let's actually add this tool to the building process, right? So I'm quickly going to do something like this, bp-inspect, right, and I'm going to try to compile the entire thing. Seems to be compiling. Okay, so that's pretty cool. So I suppose the first thing we need to do, we need to load the pairs. We need to load the binary file. We already know how to do that in bpe to dot, but the function is actually located in that utility. So we have to move it to the common part, right? So we have to move it to bpe.h, but in bpe.h we only store the declarations. So we'll have to create a translation unit for bpe.h, right? So I'm going to put this declaration in here, and then I'm going to create bpe.c, and I'm going to move load pairs into bpe.c, right? So now this implementation is shareable across all of the tools. Right, so, and it can't find this specific function in here because we don't link that translation unit with anything. So let's actually add that translation unit to each individual tool. We're going to link each individual tool with that translation unit. So bpe.c, let's go. Okay, so yeah, so now we have a problem that it doesn't know where is the boolean. So let's include bpe.h. I think I included std boolean in there. Okay, yeah, so size t, as far as I know, is located in stdlib. Still complaining about booleans, so that means we need to include boolean in here. What else do we have? String builder. Okay. So here's the thing. So string builder is located in knob.h. We have to include knob.h in here, but now it raises the question where the implementations of the knob functions go, right? So tool depend on knob, and the common translation unit also depends on knob. Where are we going to put the implementations of the knob functions? I think it makes sense to actually move the implementations of the knob functions into the common translation unit, into bpe.c, right? So because it's shared, so the bpe.c is shared and the knob functions are shared as well. So if you just include knob.h, it is not going to include implementations. For that, you need to define knob implementation. So we're not going to put implementation into the header, but I think we're going to strip the prefixes. So, and then what we're going to do in here, we're going to put implementation somewhere in bpe.c, but at the bottom of the file, so it doesn't disturb anything above, because it's C, right? So classic C. Knob implementation, and I'm including implementations in here. All right, so but now I have to remove implementations from all of the other tools, so there's no conflict of implementation. So I can just remove this entirety of the thing. I can even remove including.h because it's already included by bpe.h. All right, so this one also should not include that, and this one doesn't need to include that either. All right, so hopefully that is going to work. Okay, so this is a fucking classical problem, right? So essentially, there is a problem with stripping prefixes is that knob defines an alias for a name, but the function rename already exists in POSIX, not on Windows, but in POSIX. And this is a bug that I don't really know how to fix, but the workaround for this specific bug it essentially just undefined this specific thing, right? I mean, I could have just removed this alias, but that is going to break all of the code that undefines the rename, I think. Right, well, we can actually try that. So first of all, let me just see if it compiles. Okay, so it does in fact compile. But then if I remove this alias and I still have the code that undefines this alias that doesn't exist anymore, it is it doesn't break. This is actually kind of cool. So that means I can just remove, I can just remove this alias in the future versions of Knob. I'll need to test that a little bit more in the future, but I mean, that's kind of cool. So that means it's not going to break much. Okay, so it is fixable then. So yeah, now this entire thing compiles. Let's load the pairs. Let's utilize this entire function. BPE inspect. Right, I'm going to put this entire thing in here. We're loading them from the input file path, right? So then I need to allocate these pairs on the stack. And also we need the string buffer that is going to be used by the load pair function to load the binary from the file, right? But then we're not going to be using the bytes of the file, right? So we only need to load them so they can be converted into pairs. All right, so I'm going to put it like that. And if this entire function fails, we are going to return with non-zero exit code. Okay, so now let's iterate each individual token, right? So each individual pair represents the token, and the ID of that token is the index of that pair. So that's how it works essentially. So it's a table. So I'm iterating token from 0 up until pairs count, and I'm incrementing this entire thing. So what I want to do, I want to print the ID of the token, right? So this is the token, and then the textual representation of that specific token. So we need some sort of a function that will take a token and render it. So the way it works is that if the pair associated with a particular token has left equal to its own ID, you have to treat the ID of the token as an ASCII code. And if it's not, you basically have to recursively render left token and right token and concatenate the results together. So it's sort of like a tree, but it's not really a tree, it's a directed acyclic graph. Right, so it's sort of like a tree that intersects with itself. So that's an interesting way of looking at it. So directed acyclic graph is a tree that intersects with itself. It's a really funny way to look at it, but anyway. So let's create some sort of function, render token, and it's going to take obviously token, you insert it to token, and where are we going to be rendering it into? So we already have a string builder, so we might as well actually render it into that string builder. So why not? So this is going to be BSB, and in here again, we need pairs as well. So pairs. So if token is equal to pairs items token left. If the left element of the pair is equal to the token itself, this is a leaf, right? So this is sort of like a termination point. So we have to treat it as the ASCII code. So we have to append. We can actually treat string builder as a dynamic array because that's what it is. It's a dynamic array of characters. We are appending token as a character. And then we return, because this is the base of the recursion. So after that, we have to render left and right token separately, recursively. Right, so this is going to be token pairs. Then I'm taking the left token in here, rendering it into SB. And then I'm rendering into SB the right token. And I think that's the entirety of the algorithm, honestly. That's the entirety of the algorithm. So after that, let's actually clean up our string builder. So after we loaded the pairs, we don't really need string builder anymore, right? So it's only used for the internal implementation of load pairs, and after that, you're free to discard it, right? But what we can do, we can actually reuse whatever memory was allocated within string builder, which is rather convenient. So render token, and I'm rendering pairs. Token pointed to SB, all right. And then, so since I'm using printf, the string has to be null terminated. So let's actually append null in here. This is going to be SB, and I'm going to put SB items in here. So after that, I think that's the entirety of the implementation. So there is a little bit of a problem with render token, is that, as already said, directed acyclic graph is a tree that intersects with itself. That means it will re-render the same tokens several times. So it will do a lot of busy work. So one of the things we probably have to do in here is memorize, employ some sort of a memorization, so to not re-render the same tokens over and over again. So let me actually put some sort of to do in here. Employ memorization, so to not re-render the same tokens over and over again. Right, so I'm not going to be doing it right now, but I think this is something that would be nice to implement for performance reasons. All right, so let's actually try to rebuild the entire thing. Okay, so let's apply the BP inspect on the thing that we just created. Okay, so that works. So as you can see, so the tokens are like nested, right? So bigger tokens may contain smaller subtokens. So, and yeah, some of them have trailing spaces. Because of that, I have a feeling that we need to put bars around the text of these things. Let's actually simultaneously rebuild and run. Okay, so now we can see all of the trailing white spaces and stuff. And also there is like unprintable characters. So what we're going to be doing with them, I don't know, maybe we're going to just ignore them. So there's also new lines, get fucking damn it. Yeah, we'll need to think how we're going to print all of that. 0 is nothing. Maybe we should actually not even try to render 0, because 0 doesn't make much sense. What about just, yeah, what about just starting from 1? Yeah, 0 doesn't make sense. Okay, so what's interesting is that now we can try to tokenize something bigger, right? So because this paragraph is rather small, but what if we try to tokenize the source code of the tokenizer itself, right? So like this specific text, and see how exactly it is going to split it into tokens. I think it's going to be interesting. So let's do text to BP, right? So this is going to be src. Text to bp.c, right? And I also have to provide this entire thing. So this is going to be bp, right? So we got something, and we already can see that it's bigger than the one created from a Wikipedia page. A paragraph, it's not a page, right? It's just a paragraph. And now let's just try to inspect this table of tokens. Okay, so like a whole line as a token. So, oh yeah, this one was repeated more than one time, apparently. This is actually kind of funny. txt to bpe. All right, so yeah, it was repeated 2 times, and because of that, it became an entire separate token. It's actually kind of cool that it can detect that. So, and also this token in items, right? So this specific thing also occurred several times in here, 2 times to be precise. And there is whole chunks of code. Wait a second, this is actually kind of cool. Right, so this thing occurred several, yeah, okay. Yeah, because in parsing we just like have the same thing. And it differs in input and output, but this entire thing was considered the same. This is actually kind of cool. Now, the whole chunks of code is a separate token. So, and like new lines, all of that kind of looks ugly, right? So, and we have unprintable characters and stuff like that. So as far as I know, in C, there is a function called isPrint, which actually tells you whether the character is printable or not. We can try to employ that function in here. So let's quickly do that. Inspect. So essentially, let's split the whole thing like that, right? So I'm going to actually print F in here, like so. And after rendering the token, we have to iterate through each individual byte of the token, SB count ++I, and we're going to check the following thing: is print. If it is in fact printable, we're going to just print it as it is, as a character, nothing special. SB items I. If it is not printable, let's actually print it as a hexadecimal value, maybe capitalized one, right? But also let's convert it to uint, right? so because it's definitely not printable. And maybe we can employ the format of escaping bytes of C string, right? So essentially let's actually pad it with 0, with leading 0, and put /x, right? So we're going to be using the same syntax for this kind of stuff. Okay, and that looks kind of cool. There's addition. Yeah, we freaking multiminated this entire thing. All right, so that seems to be working, right? So that looks a little bit better. Right, so now like new lines are 0 A's, and what about the things above? Right, yeah, okay, so this is actual characters in here, and so on and so forth. So we have this additional argument that is ignored, so let's remove it. All right, so now we can basically inspect the BPA tables that we generated from text, right? So now at least it's visual, we can see what the fuck is going on. This is nice. This is absolutely nice. Okay, so maybe I want to git ignore the BPE files. I don't want to commit them into the repo. And let's now do a committee, and maybe potentially even push. Introduce BPE inspect, and I'm going to push that right into the repo. All right. So that's pretty cool. That's enough for today. Thanks everyone who's watching right now. I really appreciate that. Have a good one, and I see you all on the next recreational programming session with Mr. Azuzin. I love you.